course, at least most of us or all of us on the call should be able to understand some of the key concepts in AI and machine learning, and also get our hands busy with some of the demos that we'll be sharing. So the gentleman on the screen, I'm sure is very popular. Most people know him. He's considered to be the godfather of AI, or the father of AI. His name is Alan Turing, and he was the first person in 1950 to come up with the thought about getting computers to think. And he set up this very wonderful experiment to see if someone would be able to be deceived by a computer to think the computer is human. I think based on that idea, there's been a lot of hype in the area of AI. Most people think that AI has advanced to the stage where it can begin to have those human abilities, like the ability to create something, for example. This meme just pictures what's going on behind the scenes. Behind the scenes is actually humans that are still creating these things. It's not AI that is creating smaller AI. So, I mean, the idea of this session is just to remove that veneer of magic. Most people think this thing is magic. In fact, any advanced technology, most people consider it to be magic, but we want to see how we can let you understand what goes on behind the scenes, at least at a conceptual level, even though we'll not be going very deep into the mathematics and some of the coding aspects of it. But we'll do some demos, we'll do some coding as well, but very high level. So what are we going to do in this workshop? We're going to look at the historical context of AI. Where have things progressed from, and where are we now? We'll also look at some of the core concepts of AI and machine learning, and then touch on some of the very basic algorithms, regression and classification. We'll also look at natural language processing, which has really revolutionized the AI space. A lot of people are interacting with most of the applications that are based on natural language. So we'll touch a little bit based on that to just show you what goes on behind the scenes, or some of the things that go on behind the scenes. And then we'll touch on generative AI concepts. And okay, what we are not going to cover in this class, we're not going to cover the mathematics of machine learning. I'm also not going to the advanced aspects of it. So AI hasn't just started within the last couple of years. There's been an ongoing research area since the 1950s. Like I said, Alan Turing, with his wonderful experiment called the Turing test. That was where it all started from. And then there's been a lot of development. There was a period in the 1970s where we considered the AI winter, where things were kind of at a standstill. People were not actively researching AI at that point, but things began to pick up again in the 1990s up to present day. But within the last decade or so, there's been an immense increase in the number of innovations in this area. And those two, the two major drivers for these innovations are the computing power that we now have access to. We have very high supercomputers now that we can use to crunch data. And then the second factor that has led to the innovation and the explosion in this area is the availability of data. We now have access to more data than we have ever had as a species, right? So those two things have led to the recent boom in this technology, in this area. So that's where we are. And we've seen LLMs have taken over the whole space. Everybody's talking about ChatGPT and what it can do. But what we are going to see in this class is that the technology is not yet perfect. And that's why a lot of people are researching, myself and Joshua, for example, still seeing how we can try to make things better. So what exactly is artificial intelligence? I think this is a very complicated subject to discuss, because for it to be able to define artificial intelligence, you first need to define intelligence, which is a very complicated subject on its own. But we just look at some of the key broad definitions of AI. It's a multidisciplinary field of computer science, and the whole aim of AI is to see how we can emulate or surpass human level of intelligence. That's the I'll say the definition of AI. And a subfield under AI is machine learning, which is most of the AI that we see is actually machine learning. And then some maybe natural language processing that goes on behind the scene. But machine learning is the ability for the computer to learn from data and make predictions. So what we are trying to do mostly when I talk about machine learning is predictions. We're trying to predict either a numeric value or a category, a class, right? So those are the two broad definitions. I'll just keep it very simple at that level. Under machine learning, you still have deep learning, which is a more advanced type of technique, right, in machine learning. But I'll just keep it at that level. So for us to do AI successfully, we need this five. We need to be well grounded in these 5 different areas. So we need to have data. Now we have data. Data is abundant, but what we need to be able to do machine learning and AI successfully is good data, right? So there's good data and there's bad data. What we have most of the time is bad data that has to do a lot of it requires a lot of work, a lot of cleaning for us to be able to make something or make sense out of it. So data is very important for AI and machine learning. You also have assumptions that are based on domain expertise, right? So for you to be able to make any meaningful innovation, you need to have a good domain expertise of that subject area. For example, if you want to develop an AI for a niche area like exploration in oil and gas, right? You need to have the foundational knowledge of what exploration is all about, right? For you to be able to make the necessary assumptions you need to make to get your model to work. And then you need to have some good knowledge of algebra and statistics. I would also add calculus at a more advanced level, but these are the basic mathematics that you need for you to do AI and machine learning properly. So now I'll just be touching on the differences between machine learning and traditional programming. So in traditional programming, you have a computer that takes in inputs and then a program, and then it runs with that input and the program and then gives you an output at the end of the day, right? But when you talk about machine learning, now you have inputs and you have the outputs, and then you're trying to work your way back to get the program that maps the inputs to the outputs. So that's the basic difference between machine learning and traditional programming. So in machine learning, you're not trying to explicitly program the system and say if this, else that, and all that. Well, you're trying to get a hypothesis or a guess or how the inputs relate to the outputs, right, from your data. So that's the basic difference between machine learning and traditional programming. Now, machine learning, the classical machine learning, as I'll call it, is divided into 2 very broad groups. You have supervised learning and unsupervised learning. Now, in supervised learning, what you have is data that is pre-categorized, right, or numerical. So you have categories clearly defined. You have the inputs, and you also have the outputs given to the machine, right? And then the machine is now trying to learn the link or the nexus between the inputs and the outputs. That's supervised learning. But in unsupervised learning, you're just throwing the data at the machine and telling it, give me whatever you can find from this data. Just work out something and give me something, right? So you're not explicitly telling this is what the output looks like, right? You're just giving it inputs and then telling it to give you some kind of categorization or a mapping, right, of that data space. So supervised learning can be also further subdivided into classification and regression. So in classification, you're trying to delineate, right, between different classes of things. For example, let's say in a basket, right, you have oranges, you have apples, you have pineapples, and in each of these fruits, they have their own different features, right? So you're now trying to classify what are the features that would make me call this one an apple? What are the features that will make me call this one a pear, for example? And you're teaching the machine, right, to be able to do that classification. And you can also evaluate how well the machine is able to classify those examples that I've given to it. So you're teaching it explicitly, giving it the inputs and the outputs, and telling it this belongs to this class, this belongs to this other class. And then if you now present a new instance to it, how well is the machine able to classify those different groups for you, right? So that's classification. Regression is more about predicting a number, right? Instead of giving you classes, it's giving you a number as the output. So for example, you have a list of houses and their prices, and then the postcodes, right? And the machine learning algorithm learns the nexus between the postcode and the price of the house, right? So if you now present a new postcode to the machine, can it give you the exact price of that house, or a very good guess of that, a good guess of the price of that house? So that's what regression is doing. It's trying to predict a number instead of giving you classes, right? Like you have in classification. I won't be touching more on the unsupervised learning because I think it's a little bit more advanced. Maybe in subsequent sessions we can dive deeper into that. But we have things like clustering, association, dimensionality reduction in unsupervised learning. So AI has a lot of applications. I'm sure all of us have used AI today in one way or the other, whether it's your text completion in your Microsoft Word or your iPhone, right? Those are all applications of AI. Optical character recognition, a lot of us have used this to scan documents and PDFs. We also have recommendation engines. For example, your Netflix can recommend new movies for you to watch based on the ones you've already seen, or your Amazon Prime, right, can recommend something for you to buy based on what you have purchased in the past, right? So those are all recommendation systems, applications of AI. Autonomous vehicles, right? We have two very notable companies working on this problem, Tesla and Waymo. Even though this problem hasn't been fully solved, but we've had a lot of how do I say, a lot of innovation or progress in that area, right? Facial recognition, a lot of us have used iPhones or have iPhones that we make use of facial recognition systems. Yeah, there are a lot of applications. So I'm sure if you just think for a minute, you know that you've used some of the AI out there today. So when we talk about AI or machine learning, why exactly are we trying to learn, right? Why do we feel it's necessary for machines to learn, or what are the things that we feel we'll be able to achieve, right, from machine learning? And I've put some examples here where human expertise does not exist. For example, navigating Mars, no human has been able to, land on Mars or do like live or exist there naturally. So you have a lot of exploration that you can do there. You can send robots there, get data, and then analyze it and use it to gain expertise of that terrain. Another place is where you're unable to explain their expertise, when humans are unable to explain their expertise. So a lot of us, we think we know what we are doing when we are speaking or when we are communicating, right? But we can't really explain it at a very deep level, right? So when we try to learn using machine learning, we're trying to understand what exactly is going on in the human brain, right? When we are communicating, when we are speaking to somebody, maybe in the same language or in different languages. So yeah, trying to explain naturally occurring things, right? You're trying to now abstract it based on what we have. The other application, why we learn, solution changes in time. For example, routing a computer network, that's a time series based activity, right? So we need to be able to understand what's going on. Yeah, and then the last one, when the solution needs to be adopted to particular cases, for example, autonomous driving, or maybe your business, for example, right? You can apply machine learning in your business. If you have a company, let's say you can apply machine learning to get the sentiments of your how your users view your business or view your products or services, right? So those are all areas where we can apply these things. And then what do we really mean when we talk about learning as regards to machines, right? So what the machine is really doing is just trying to get a hypothesis or a guess, right? Um, so when we're trying to generalize based on the examples that we've seen, that's what the machine is doing. It's trying to generalize based on examples it has seen. So if you say a cat has this dimension of ears and this dimension of eyes, for example, if you give it many images of cats, right, it can, I mean, predict at a very good level, right? Give a very good prediction of what a cat will be. And if you give it a different thing, let's say a monkey, it will tell you, no, this is not a monkey, this is a cat, right? So it's trying to help the machine to make a prediction or make a guess. That's what learning is. It's all about when we talk about machine learning. We've talked about the different ML applications, supervised, unsupervised, reinforcement learning, right? So that's just at a very basic level what we're trying to do when we talk about learning. And then for these machines to learn, at least we know that computers deal with numbers, right? At the basic level. So whatever it is you're throwing to the computer, whether it's text, whether it's speech, whatever, video, it all converts everything to numbers, right? And uses those numbers to work out or compute a result for you. So we have to be able to represent this data and push it to the computer in the appropriate format. So, for example, the example I gave about categorizing fruits. So you have an orange. This orange, we call it an instance, X1, for example. We have a banana. We call this banana X2. So the orange has some characteristics. It has a color, it has weight, the average weight of an orange, right? And then it has, let's say, a texture. So we can now assign values to each of these features. We call them features. The color, the weight, the texture. We call those things features in machine learning when we're talking about data representation. And then the prediction from this our learning, we call it the outputs or the targets, and that will be Y. So when you have this kind of problem, you have to be able to represent it in a way that the computer will make sense of it. And that's what we're trying to do here in data representation. So we have, like I said before, different fruits. You convert them to this kind of representation, and then you have the coders do some magic with it, right? Yeah, so this is the process of machine learning. You have a training set, right? What you use to teach the computer, a set of data that you use, let's say in a categorization problem or a classification problem, you have the training set, which which is composed of the inputs and the outputs, right? And you're presenting that to the computer to work out a hypothesis or a guess for you, right? And like I've just explained, the training set gets fed into the training algorithm, and then it produces that hypothesis for you. So you can now use that to generalize going forward. When you have new instances, you present to the computer, and then it shows you what category or value should be assigned, right? So I'll not be touching more on that. I'll just go down to what we mean by generalization. So in generalizing, you're not just looking at individual instances now, but the ability for that's your model to generalize, to be used in more than the training set that you've given to it, right? So when you train the machine with a specific pool of data, right, you keep that pool of data aside, and then you bring a new instance, right, that is not in that initial pool that you use for training. Is the machine going to give you an appropriate guess based on what it has learned from the initial pool that's used to train? I don't know if that is clear. So you're not looking at individual instances, that's f of xi now, but you're looking at f of x for the entire set of new data. Can that machine give you appropriate of guesses or predictions. So that's what we talk about that's what we mean when we talk about generalization. The ability for the computer to give us the appropriate prediction based on the training it has done in the past, for it to give us the appropriate prediction for new data that it has not seen before. That's generalization. If it's able to do that, then it has generalized properly. Right. So the simplified picture of machine learning, you have your training sets or training data. You have your training labels, which is the outputs. So you have the inputs and the outputs, and then you feed that into the model. Right. So if the model is able to learn from that input and output, right, we say that the model has trained, right? So that's the training completed. Now, we now bring in test data to test the understanding that this computer had in this initial training phase. We bring test data to it. If it's able to predict appropriately, right? That's the evaluation part now. If it's able to predict appropriately based on what it has learned here, if it's able to predict for this new data, this test data, if it's able to predict for them, then we say it as generalized. That's just the picture of machine learning, right? So you have a particular set of data that you use for your training, and then you bring in new data that it has not seen before. If it's able to give you appropriate predictions, right, for that new data, then we say it as generalized. That's just the simplified picture of machine learning. So I would just like to pause a bit here at this point. We've touched on categories of machine learning. We've given you some of the main concepts, how we represent data, and then the concepts of hypotheses, the labels, and the features vectors. So I don't know if there's anybody that has a question at this point. Can quickly take it.
Okay, thank you, Abu, for the section. We'll take those questions together towards the last part. So,
okay,
do you?
Okay, let me go on then. Okay. Let me go on then. Yeah. So that's it for machine learning. It's a very brief introduction, just for the main concepts of machine learning, what we're trying to do in machine learning. Now I'll take you through natural language processing. The reason why we've introduced this section is because of how this training has been structured. So we want you to be able to do some hands-on stuff at the end of this training. But we need you to understand what goes on behind the scenes, right? When you're interacting with an AI in natural language, right? What is the AI doing behind the scenes? That's why we've introduced this, right? So language is a very important and interesting concept, right? The ability to communicate, be understood, is very important, and that's why the improvements that have been made in this area have been tremendous, right? And everybody is talking about it. So what are some of those things that the computer does behind the scenes, right? When we're interacting with it, natural language processing, that's what it does. What are the tasks under natural language processing? You have things like tokenization. When we say tokenization, we are trying to split up the sentence or the paragraph or the book, right, into individual words, right? So that the machine, I told you earlier that the machine deals with numbers, right? So we're trying to now split everything up into individual words so we can later apply some machine learning around it. Sorry, I saw a hand up just now.
Sorry, just go on, please.
Okay. So that's what tokenization is about. The second concept is the embeddings concept. So for embeddings, what we are trying to do is to group those words, right, to split them up into different groups. So this simple example here, I have the highest respect for your nerves. They are my old friends. So this is an example of word embeddings for a sentence in the book called Pride and Prejudice, right? You're trying to split those words up. Now, you're not taking them individually like you do in tokenization, but you're kind of grouping them a bit. The other part is passing and part of speech tagging. So here, like every language, you have parts of speech, you have verbs, you have nouns, you have adjectives. So you're going to put in tags, right, for those different parts of speech in your corpus. What I mean by corpus is the body of knowledge that the machine is using to learn the natural language of that particular language. So this is just an example of what that tagging is all about, the parts of speech tagging. Yeah, then the other thing that we do in natural language processing is word and phrase frequencies. So each word, there's a score of how frequent that word is used. An example of this is, I mean, a very direct example of where this kind of method is used is in sentiment analysis, where you're trying to get the overall sentiments of a text, right? You can now say, okay, the number of positive words in that text, right, means if I have a higher number of positive words in that text, that means it's positive sentiments. But the machine can be tricked in that regard, because you have things like sarcasm in English, for example, where you can use positive words to say something very derogatory, right? So how does the machine do that? There are more advanced concepts, but we'll just keep it simple at that level. So word frequencies, what's the word count, right? How many times does words appear in that body of text? How many times does moral appear, for example? Yeah, so then there's also the concept of n-grams, where we talk about n-grams, the number of words, right? You can split your text up into a group of words, right? So like this one, the quick red fox jumped over the lazy brown. So you can be picking, let's say in groups of 3, picking words from that text and then using it to do some analysis later on. Then the other one we try to do is lemmatization. Lemmatization is just simply getting the root word, right? For example, flew, flies, and flying have the same root word. They have the same lemma called fly, which is the root word of all these things. So you're trying to understand what words mean, or the machine is trying to understand, and you're helping the machine in that regard. So when we do all that, we now apply some machine learning in NLP. I've told you about sentiment analysis. And then I'll go briefly, just very briefly, about the large language models, which is the rave of the day. So what are LLMs? LLMs, these are massive data sets, right? Models that have been trained on massive data sets to achieve very advanced language processing capabilities. So the same natural language processing, but at a more advanced level. For some LLMs, they can have up to 70 billion parameters, for example. Those are things ranging from all the stuff I've shown you, the tokens, lemmatization, all those things, 70 billion of those type of properties. And the machine is crunching all that data and trying to make sense of what you're presenting to it, right? So there's some deep learning that goes into that as well. And then we have foundation models. These are your GPT-4, the BARTs, NPT, 7B. Yeah, so this 7B means 7 billion hyperparameters. So those parameters, 7 billion of them, that's what has gone into that model. And you can see these models are very large. So that's why we call them large language models. So a very simplified view of what goes on in your large language model. You have your inputs, and then it's tokenized, right? And then you now have token embeddings on top of that, right? So all of this goes into what we call the encoder. Because LLM uses what we call generative AI, we have what we call the encoder and then the decoder. So the encoder takes in natural text, which is your inputs, and then tokenizes that, right? Converts everything to numbers at the end of the day and gets your embeddings. Embeddings is more like your the similarity between text, right? You're trying to see how similar texts are occurring in that body of language or whatever. And then that encoder gives an output, which is more like, it's just I don't know how to explain it in, in layman terms. So it's more like, I just have to make use of this word, a latent space. So latent space, for example, can be okay. I think maybe we should just go silent on this one, because if I need to explain it, I'll need to go a bit technical. So I'll just be silent on what goes on at this middle place, right? But we know that some computation goes in here, and then at the outputs, that number that you converted in the encoder now gets converted back into text, right? And then it outputs it to the user. So when you're chatting with an LLM, this is what goes on behind the scene, right? The encoder takes in your text, converts it into numbers, does the crunching for you, the mathematics and all of that, and then outputs a result in plain text, right, from the decoder. So this encoder decoder system is what the generative AI really works with. And so we have a lot of LLMs out there today, and we can categorize them into open and closed source. So the open source LLMs, they are free to use, right? And we'll be using some of them in this workshop. They are free to use. The advantage of open source LLMs is that you don't need internet. You don't need to have internet access to make use of them. The disadvantage is that those LLMs were built at a particular date. So sometimes they can be stale, right? Because the world is quickly advancing, information is changing every day. So maybe if you downloaded your LLM as at March, for example, some of the information there would have been stale. So if you use it to build anything, it might give you wrong outputs, right? So that's just the thing about the open source. For the closed source, things like your GPT-4, ChatGPT, those are all closed source because you have to pay to use them, right? And so, yeah, I think this is where I'll end my session. Just a quick recap. We've talked about some of the tasks common to NLP and some of the applications of machine learning in NLP. And then we've also discussed the large language models and the open and closed LLMs. We'll still touch on some of these things in the later sections when we are doing the demos and the hands-on. So I'll allow Joshua now to share his slide. He has a little demo for us this evening. Joshua, thank you very much.
No problem. Thank you so much, Mr. Abo. A very wonderful session. Very well put and well described. Very beautiful. So we'll move on to the next section. When we were kind of concepting and planning for this, we were well aware that not everyone who will attend will be from a technical background, whether it's coding or the hard mathematics. So we were trying to structure it in a way that everyone who attends can benefit something and gain something from it. Because in truth, when you see AI today, even if you don't have that necessary coding background, you can still interact with it in different ways. So we're trying to kind of factor that in. So we'll go over some bits of AI. It will be a bit more simplified, but it will still touch on a few of the things we're going to do today, in particular in regards to the training of the slight model we're going to do later on as a practical activity. Don't worry, it won't be a long session, to be a fairly short one for this one. Let me just share my screen and get my slides up. I think that should be it. All right. So from beginning. All right. All right, so we're going to be training an AI model. Like I said, a lot of things we've kind of simplified a lot. So the first slide you see, don't be scared, don't be intimidated by the code and start running away. I just need to show, a small example of a model being trained. This is just a snippet of code from one of the samples we're working on, just like teaching a model to identify tumor. So it looks at the cancer tumor, and it, based on the data it has, it tries to determine, okay, fine, is this tumor cancerous, or is it no longer cancerous? So, but the reason why I put this is just so that as we go through the rest of the simplified version, to bear in mind that even though we've simplified a lot of the key concepts, there's still a lot of maths, a lot of calculation, a lot of coding going on behind the scenes, similar to what Mr. Abu described with the language models, where you just talk to ChatGPT, give me 5 fun movies to watch. For you, you're just typing a text, but behind the scenes, there's a lot of different calculations and coding going on. So we're going to be using something called a generational model. To begin with, we'll take a scenario. Let's pretend, you just opened your new restaurant and you want an AI model that can cook for you your chicken. Let's call it, Chicken Master 2000 to give our model the name. So you want it to be able to create the perfect chicken for you, if that makes sense. So, but to begin with, first of all, we've mentioned model a lot. I just want to explain what a model is in regards to AI. In the simplest basic term, a model is simply a program that uses AI techniques to make decisions. In the most basic term, that's how you describe a model. It uses AI techniques to make decisions. It could be predictive decisions, trying to predict something, trying to recognize patterns, but in the most basic form. So if I go back to my previous slide, when I say a generational model, remember a model is just an AI program. So you're just saying this is an AI program, and the technique it uses is called a generational technique, if that makes sense. Yeah. So in its most basic term, an AI model is just simply a program that uses AI techniques to generate and make decisions based on data. I put that in quotes because all models are trained based on data. And what is training is also a key concept in terms of AI. Training is just as simple as, I guess, how we create AI programs in the most basic of terms. AI training is just you creating an AI program, because it's through AI training that we teach our AI what we want it to do and how we want it to test itself and grade itself, and so on and so forth. So to go back to our example, our scenario, our Chicken Master 2000. So we have our AI model here. This is the little machine. And we have our desired outcome. We know what a cooked chicken looks like. Our AI has no idea what a final cooked chicken looks like. So to simplify our scenario, we will pretend everything else remains the same. The seasoning remains the same. The oven remains the same. The only thing that we will change in this example is the temperature, because we don't want to work with too many variables, so the explanation doesn't get too complicated. So every single thing will remain the same except the temperature. So this is our AI model. We have our, our desired outcome. This is the data we're going to give it of what a final piece of chicken looks like. So from here, how do we teach this AI to cook for us this perfect chicken at the right temperature? So we will.
Brother Joshua, it's like we're still seeing the first slide.
Oh, really?
Yep.
Okay.
Okay, now we have the second slide.
And then you can make it a presentation mode.
Oh, I see. Okay, apologies. I've seen the mistake. Apologies. There we go. This should be better now. So are you seeing the next slide now?
Yes.
Yeah, apologies. I think I shared the wrong screen. So I'll just do a very brief run through. I won't go into too much detail, but this was the code I was showing of, a simple training of a using a logistic regression model. Like I said, a model is just simply a program that uses AI techniques to learn in a very basic term. And this particular program was using a technique called logistic regression to learn. So this is just an AI program that uses logistic regression to learn. So it's trying to identify breast cancer tumors. So we will be using a generational model for our example today. And so just the scenario, we have our AI model. This machine here represents our AI model, just to have something familiar that we can relate to. We called it Chicken Master 2000, just so we have a familiar name. Rather than saying our model, I can just say the Chicken Master 2000, and it'll be a bit more familiar for us to understand. Again, these are the key terms in the slide. Like I said, a program that uses artificial intelligence techniques to make decisions based on data, and training is just simply how we create AI programs. So this was the slide of me showing that we have our model and we have an example of our desired outcome. This is how we want our chicken to look, our finally perfectly cooked chicken. This is our example, the data we're going to feed the AI to tell it, okay, fine, this is what we want the chicken to look like. Learn the final temperature, not find, learn the final temperature. I will explain more in that as we move along. So how our model, look at our model in the corner, assume we've zoomed into our model. This is us inside our model right now. How the inner bits of our model works is, it doesn't know the perfect temperature to cook that chicken to get it at the right result. So what it does is it's gonna create, we'll call it a bot for the sake of lack of a better term. It will create a bot. This bot also doesn't know what the temperature is, but what this bot can do very well is it can build other bots. It's a bot building bot. It can build a bot that can cook chicken at 3 degrees. It can cook it at whatever degrees it wants. So it can build a bot that can cook chicken at whether it's 3 degrees, 4 degrees, 100 degrees, 500 degrees, whatever. For the sake of this example, we will assume the bots can only pick 1 degree. They cannot change that degree. Once they've been created, that degree that they were created with is what they will stick to. So this bot, for example, in this example, it can never cook above 3 degrees or below 3 degrees. That is its final, its only degree, if that makes sense. So this builder bot is very good at building bots. If you tell it build a bot that cooks at 70 degrees, it will build for you that bot perfectly without an issue, very smoothly. And this oven bot, all it does is it just cooks chicken at the degree it's been taught to cook at. So 3 degrees, it just goes and cooks it at 3 degrees. Remember, none of our variables change. The time remains the same. The oven remains the same. The only thing we're changing for this example is the degrees we're cooking the chicken at. So it will go put the oven put the chicken in the oven maybe for an hour for 3 degrees. They now bring back and tell you, okay, fine, here's my final result. I've cooked your chicken to the best of my ability based on how I've been built. So this just explain that the temperature is what it changes. But remember, both of these bots have no idea what the perfect temperature to cook a chicken is. This bot can build many bots. It can likely build a bot that will get the perfect temperature, but it still doesn't know what the perfect temperature is. So for our model to achieve this, it has to introduce one more bot. And it's now bot. It has to introduce one more bot. I promise it'll all come together very neatly at the end once we have all the bots relating to each other. This final bot it will build, we'll call it a teacher bot. Now, it's not teacher in the traditional sense that we understand the word teacher, because this bot can't teach, because it's also a bot that has no idea what the perfect temperature is. But what this teacher can do very well is it can give tests. It's a very good teacher at giving tests. So it will come and say, okay, fine, oven bot, cook for me a chicken that looks like this. Remember, this chicken, we gave this chicken to the teacher bot. This was our initial data that we provided our model with. This model here, we told it we wanted a chicken that looks like this. So the teacher bot can't teach, but it can grade very perfectly. If you give it 2 chickens, it'll say, okay, fine, this chicken does not look like the one I've been given by my human that says this is the perfect chicken. So it can grade very, very accurately. So using this, the teacher bot will now tell the oven bot, cook for me a chicken that looks like the one I've showed you here. The oven bot, to the best of its ability, remember it can't cook above 3 degrees. To the best of its ability, it will try and perform that task and come and say, okay, here, I've cooked this chicken to the best of my ability. What do you think? The teacher bot will take this chicken and take the one we provided it with. Remember, we had given it a labeled data of what a perfect chicken looks like. It will take the 2 of them and it will now mark the test and say, okay, fine, based on what I know is the correct answer, how much do I score you as? In this case, let's say it scores him, gives him a grade of 5%. You know what? Your chicken still looks raw. It doesn't have any flavor. We don't like how it is. So I'll give you a score of 5%. So to go back and recap, we have a builder bot. It's very good at building bots that can cook chicken. We have an oven bot. All it does is cook chicken. It doesn't know what the right temperature is, but all it can do is it can cook chicken and cook it very well. And we have a teacher bot who can teach, but can give tests very, very well. It's very good at giving tests. So using these 3, I'll explain to you how the AI model can learn to find the perfect temperature to cook our chicken using these 3 bots and this series of bots. So if you go back to our example, the builder bot will then build. Now, instead of building just one bot, it will build a series of bots. For this example, let's use 9 bots. It will build 9 bots with different parameters. So the little numbers below them represent their temperature. So this one can cook at 3 degrees. This one can cook at 1,000 degrees. This one can cook at 15 degrees. It can give them the numbers randomly, or if as humans, because we build this bot. If when we're building the bot, we can maybe give it set of rules to follow when building the bots. That's up to us to decide as the programmers. So it will build 9 bots and tell the teacher bot, hey, I've just built 9 bots trying to cook the perfect chicken. Give them tests and tell me what you think. So the teacher bot will say, okay, lovely, give me your 9 bots. It will take all of them and give them that same test it gave our first bot. It'll say, all of you, cook for me a chicken that looks like this. Now, all the bots, to the best of their ability, remember, this guy can only cook 3 degrees, this guy can only cook 1,000 degrees. To the best of their ability, they will try and achieve this desired result. So they'll come, they'll submit their results. This guy will say, okay, fine, here's my chicken. This guy said maybe it was too high, it burnt. This guy said maybe it's still raw. And all of them will submit their results. Don't mind that the photos are similar. I'm just trying to I was trying to explain, but don't mind that all of them have burnt chicken. I know chicken doesn't necessarily burn at 200 degrees, but it's just to give an elaboration. So the chatbot will grade all of them and say, okay, fine. I have an example of a perfect chicken from my human. Let me grade you and see how well you match this perfect chicken. So it will give all of them different test scores. Each one of them will have that test score. For this, I just gave only 4 of them grades, so I don't have the slide looking too busy and hard to follow. So it will mark all the robots, and then it will pick the 3 highest ones. It can be the 2 highest ones, the 10 highest ones. Is up to us to decide as the programmers. But in this example, it will pick the 3 highest ones, and it will go back to the builder bot and say, hey, from all the bots you built, these are the 3 that performed the best. It gives them the builder bot and says, build for me more bots using these guys as your starting point. So use them, and from what they know, use them to try and build new bots. So if I go to the next slide, I'll explain that in a bit better. So it will take the 3 best performing bots and try to use it to build a bot that can get the perfect chicken. So this can be in different ways. It can be in slight variations. So maybe it'll say this one was 115. It was close but not close enough, so I'll increase the temperature a bit. For the next one, maybe I'll decrease the bit. For the next one, I'll increase the bit. So it now builds 9 new bots based on the parameters from these bots. And it will now send these bots again back to the teacher. So remember, these bots were the top performing bots from the previous generation. So now it's building a new generation of bots based on the top performers. The ones that didn't perform well, we just discard them. We have no need for them. So that's how the generational model works. It keeps building new generations by taking the best performance of the previous generations and slowly building on them. So it will go back, they'll go back to the teacher bot again and say, okay, fine, here we have a new set of bots, grade them. The teacher does his grading, says, okay, fine, these new 3 guys perform the highest. It goes back to the builder guy and says, okay, fine, I still don't have the perfect chicken, but these are the 3 best guys from the last generation. Give me a new generation using these guys as your starting point. And the loop goes over and over and over again. And because we know how, if I just go back to my previous slide, because we know the perfect temperature for cooking chicken, let's assume 165, for example, we know that this guy will keep eventually either increasing or decreasing, and same thing here, to the point where eventually one of the bots, after the loop has gone over and over and over many generations, we will eventually have one bot that can cook the chicken really, really well. Because as they've been going through different generations, the weaker ones have been discarded, and the ones that have been getting close keep getting used to produce newer ones, and eventually we settle with the chicken that can create for us the perfect bot, if that makes sense. So like I said, this is a very simplified example. We're using only one variable, just temperature alone, to try and find the perfect temperature to cook the chicken. Everything else was the same, seasoning and everything, and then we just keep building generation upon generation upon generation. But in a more accurate representation of the example, here the only variable that changes is the temperature. In a more accurate one, a lot of things will change. Maybe the bot's time will change, the time it cooks the chicken in the oven. It might cook a different part of the chicken, because at the end of the day, the teacher is saying, cook for me a whole chicken. The bot doesn't know what a whole chicken means. So it maybe one chicken will take the leg, one chicken will take the breast, one chicken will take this, one chicken maybe will try washing the chicken. Then the teacher's job is not to evaluate, okay, fine, this part you gave me, does it really match the label data I've been given? And so on and so on. It will continue going. Again, a similar thing with the builder bot. In our example, he builds just 9 bots, but in a true accurate model, you will have hundreds, maybe thousands of bots per generation, because this scale of 9 is just too small to achieve a result. Because we had just one variable, temperature, yeah, maybe we will get some our answer after a while. But if you're trying to teach deeper things, 9 bots is just not enough. So we'll have hundreds, maybe thousands of bots per generation. Again, a similar thing with the teacher's test. In our test, it was just giving one test. Okay, fine, cook for me this one chicken. But in a more accurate model, the teacher can give tens of tests, hundreds of tests. It really depends on what we're trying to build. So the teacher can say, okay, fine, cook for me butter chicken. You know, here you can see the chicken is diced. So the bot will have to understand, okay, fine, which part do I use to dice the chicken? Here's chicken wings. The bot will have to figure out, okay, fine, which part is the chicken wing? So that the teacher can give hundreds of tests. These tests can be determined by us as the humans in order to achieve whatever particular goal we're trying to train that AI model to achieve. So it will keep testing and testing and testing different hundreds of tests. How do I cook buttery chicken? How do I cook chicken wings? How do I cook a whole chicken that is maybe with a smoky flavor? Maybe it's been overcooked a bit to have a smoky flavor. How do I cook this? It will keep on doing these various tests to the point where when you, the user, comes and says, hello, Chicken Master 2000, you know, I want to make a chicken. I don't have an oven available. I only have thyme, salt, and pepper. The Chicken Master, based on the different bots it has tested in very different ways, you have to say, okay, fine, even if you don't have an oven, here's how you can cook your chicken. Even if you have only salt and pepper, here's how you can cook your chicken. And with that, we'll now have our AI model, which has trained through a generational model, so to speak. So once again, like I said, it was quite a simplified example, just to give an example of what training an AI can look like, because the practical example we will do today, it's quite simplified. So you may not necessarily understand the behind the scenes, because I don't look as if, okay, fine, you just come, press a button here, press a button there, and you're done. Even though that's what we do, behind the scenes, there's a lot of calculations, math, and programming going on. One more very quick thing before we move forward. Obviously, in our example, we were using a generational model. I picked it more because it's an easier one to understand, telling you, okay, fine, 5 bots try, the 2 that do well get picked. It's very easy to understand, it's very easy to follow. In current AI, the more used methods are things like neural networks that Mr. Abu mentioned, and deep learning. So the generational model is not necessarily, it can still be used, but it's not necessarily what is being used at the moment. The more deep ones that are being used are neural networks. So I will just give a very, very light touch on how you can understand neural networks based on the example we just gave. Right? It'll just be a very simple, just a very, very test introduction in that mission, because to go into neural networks properly will involve a lot of technical details, which I don't want to overwhelm us with. But in our example, if you remember, we had hundreds of bots, and each bot had a different parameter. Maybe this bot had a temperature of 100. Oh, sorry, here they're all the same, but they're meant to be different. Maybe this bot was cooking at 5 degrees, this bot was cooking at 6 degrees. So each bot has a different parameter because we have hundreds of them. How neural network works is, instead of having hundreds of bots, each with a different parameter, we'll have just one bot. And that one bot will have a bunch of different, let's think of this as tuning. You know how you tune a radio? We will have different tunes. So maybe this first one represents temperature, the next one represents cooking time, the next one represents chicken part. So it will have just one bot with 100 of different tuners attached to the bot's brain. So the teacher will give the bot a test and say, okay, fine, how do I cook this? Then our builder bot will adjust this parameter and say, okay, fine, let me tweak them.
Hello, Brad Joshua, your slide
Yes.
is not moving.
Is it moving now?
It's not. Yes, it's moving now.
Okay. So the builder bot on the right will adjust the different dials to try and adjust it to a point where the bot itself can answer the test correctly. So this is just better. It allows for a few more things to be done better. It allows for allows for a few things to flow easier compared to the generational models, without going too deep into the technical details. But this is a more accurate representation of how a lot of current AI models would be trained. Just to link it to an example, the generational model, it's just easier to explain and easier for people to follow, because if I started with showing dials, it may have been a bit tricky to explain some of the key concepts. So that's me just about at the end of my slide. Just before we go to the training, practical training, I just want to tie it in with some of the key concepts, because if you remember, Mr. Abu was explaining supervised learning and unsupervised learning. So the example we just gave right now will fall into the side of supervised learning, simply because we went to our AI model and told it, here is what a perfect cooked chicken looks like. Because we have given it data and we told it what that data is. Here's a photo, and this photo is a perfectly cooked chicken. That is us labeling our data. So now the AI knows what it's working with. Whereas unsupervised is a scenario where we've not labeled the data. We just said, here's a bunch of data, maybe figure something out from it. A good example could be the housing prices one. Let's say we have a bunch of data. Maybe we have how many bedrooms, how much people pay for rent, how much people live in, and we're trying to figure out, what determines the increase in housing prices. Just go and grab all that data, we put it into our model, and then we train the model using different techniques to try and figure out, okay, fine, based on all the data I have, what patterns can I find that determine how much people pay for their house, if that makes sense. So just to explain the difference between supervised and unsupervised. Supervised is where we label the data by telling it what the data is, whereas in unsupervised scenarios where we don't have the data labeled. So again, to explain two more things, just briefly before we go, evaluation and performance. In our example, evaluation was simply the teacher giving the bots a test and saying, oh, you did well was 5%, 5% was your teaching grade. In actual machine learning, evaluation and performance looks different. It can look like this now. Evaluation, it's a lot of mathematical tables, lines of best fit, trying to see if did the AI model did it achieve what you wanted to do it well. Because like that in this one, yes, it achieves it. That's in number two. In number two on the left, it achieves it, but the line is too complex. It can take a lot of resources, which is not really ideal for us. Number three achieves, but doesn't really group the data well. So we now go with number one. But just to explain that, despite how simplified we've made some of the sections, behind the scenes, there's a lot of deeper bits going on. Because even the 5% test score, this is what a 5% test score that our bots were given would look like, us trying to gauge the performance measures of the bot. So I will end my slide there and we'll go into the brief training. I will send the link I'm going to use. It's a very lovely resource. It's free for anyone to use, really. I'll show you how to use it so you can also try it maybe on your own at home or whatever, just so you have fun with it. So let me bring in the model. I believe you can still see my screen.
Yes.
Okay, perfect.
Yep.
Perfect. So it's called Teachable with teachablemachine.withgoogle.com. It was developed by Google just as a way to help people understand training an AI and showing them different ways AI can be trained. So what this one does is it's an image trainer. It uses neural networks, not the general techniques, the neural networks, and it tries to help you to be able to identify between two images. There's several ones. I'll show you the different ones, but I'll just focus on the image one for today. One thing I will try and ask is I'll have lots of ask you to send in photos of cars if you have any, so we can test. If you have any on hand, just prepare to send in. I wanted to tell you at the beginning, but I forgot. But I'll show you how to do the training. It's very, very simple. So we'll click on Get Started. So we now have, like I said, the three different ones it does. You can do image projects, what we're going to do. You can also do audio projects to help it to train an audio AI model, and also one that learns poses. But we're going to do one that learns how to decide what an image is. So I'll open this one. I'll go with the standard version because that's the one we want to use, a standard version. Actually, let me just go again because I think I did that a bit fast. So I'll click on image project and I'll pick the standard one. That's the one we want to use for this. So we now have two classes, the training and the preview. All the classes are it. Remember in our example, we gave the AI a photo and said, here's a chicken, here's a photo of a chicken. So we're going to give it photos and we're going to tell it what these photos are. I'm just going to click here and edit the name to say a car. And our class 2, let's say an airplane. So essentially, we're going to be telling it all these photos we're giving you. It's something that we humans call a car, identify them. And all these images we're giving you something that we humans call an airplane. So after you have used these two classes to study, when I give you an image you haven't seen before, try to determine, is this a car or is this an airplane? You can add as many classes as you want down here, but for this, we'll just use just 2. So I'll click upload. I have my data set. Let me see if I can show it to you. I have my data set. No, the wrong one. No, it is the right one, actually. Yeah, so I have my data set here. So I have a bunch of images of cars. I used 20 images. So as you can see, we have cars in different ways. We have a car that shares two cars in one image. Some of them is just a car alone. Some of them is a car in the rain. So this is what the AI will try to use to learn what a car is. And then we have images of planes as well. This plane is flying over a sea. This plane is flying over a blue sky. This is a plain blue sky. So we'll give these images to it so it can learn. And we have what we call our test data. This is what we're going to give and say, okay, fine. Based on what you've learned, can you tell me what this is? Can you tell me what this is? Can you tell me what this is? And so on and so forth. So I'll just click upload on my website. I'll click upload. I'll choose upload files from my PC. And I'll go back into my car. Remember, the car is the images of the car. So I'll select all 20 of them and say open. It will load it. And I'll just give it a second. And I'll go to my airplane and do something similar. I'll say upload. I choose the files from here. And I'll go out and now select my airplane. So my airplane. So now I have my two classes, one with airplanes and one with cars. Before I train the model, there are some advanced settings here. We don't necessarily need to adjust them. This one can help. Remember how we used to go through several generations in our example of the chicken, where we'll go through several generations. You can kind of think of this as generations in a way. It's not exactly the same, but you can kind of think of it as in a way. It's not exactly the same. If you click, I can try to explain to you, but so I don't get into too much technical detail, I won't because the neural network, it works by splitting the data into different epochs, so to speak. But either way, I won't confuse you too much. So, but just in case for those who are a bit more tech savvy and want to dive deep into it, you can feel free. It just tells you what it is here and here. So we'll train our model. We'll give it a second. It shouldn't take long, maybe just about 30 seconds or so. But just in case, I have one pre-trained. Okay, that's it. I think that's it already done. Even perfect. Is that it done? Model trained. Okay, that's it. Perfect. So now we have our model trained. It should be able to identify what a car is and what an airplane is. So to give it tests, now we have become the teacher. So to give it tests, we give it tests from here where it says input. Now it's trying to get an image from my webcam, but I don't want that. I want to upload my file. So I'll click here and change it to file. So remember, if we go back to our test data, we have this car here. So I'm going to feed it this car image. And hopefully, if it has trained well, you'll be able to tell me that this is a car. How it does it is by it will tell you, from what you have given me, this is either 100% a car, maybe it's 30% a car, 30% a plane. That's how it will give us our answer. So let's upload our file and see what it thinks. So I'm going to go test data. Let's select our car and say open. Perfect. You see, based on what has learned, it's telling that this is 100% a car. It is very sure that this is a car. It has learned what cars look like based on all the images we gave it. But remember, even though for us it's just a simple case of click here, click here, click here, click here, behind the scenes, the Teachable Machines site have their own neural network that they've used to train the AI model based on the label data we've given it. So we'll try one more example. Let's try one more example and see. Let's try a plane. I've not tried a plane yet. Let's try a plane. Again, it's 100% sure this is a plane because it has used these 20 images we supplied it to identify and understand what an airplane looks like. How does an airplane function in various different scenarios? So this is a simple example. I mean, identifying between a car and a plane may not necessarily be too, you may not have any practical need for that, but in real world applications, ways a simple image certain AI can be used is in things like quality control. For example, imagine you're I don't know, maybe you develop products and you sell lampstands and you want to be able to tell, okay, fine, is this product damaged or not? You can have a simple image, a simple camera that takes photos of the image as they pass through a scanning belt. Then your AI will quickly tell, okay, fine, is this image damaged? Maybe it spots a crack because you've trained on how to identify cracks. And it says, okay, fine, this image is damaged. I'm gonna kick it off the control line. Again, self-driving cars, Tesla, all of them. When a pedestrian is walking on the road, because Tesla uses cameras it uses Teslas for its cameras to understand the surrounding. So if you're driving your Tesla and then there's a pedestrian on the right hand side, how does it identify a pedestrian? Again, it's through an image line AI. It has gotten hundreds, thousands, millions of photos of what humans look like in different scenarios. A human that's bending down, a human that's crouching, a human that's on a bicycle. Then based on what has been trained, you can say, okay, fine, what I see here is a human, I should stop. One more example again in medical practice. There's a lot of ways it can be used in it is being used in medicine even. Say for example, someone that has an X-ray, then the image sorting AI has been trained to identify whether it's fractures in the X-ray or trained to identify tumors, etc. So again, this is a very simplified model, but it has a lot of real-world practical applications and a lot of ways it can be used. Sorry, I just see some questions in the chat. I will just, because I'm just about to end my session. I don't know if I should take them now.
Yeah, you can quickly take those questions. I think they are related to what you're saying. The first one is saying that, how about a text of a car and a plane
as a single
image?
So okay. So for that, I shall actually Photoshop one to show you. For that, what will happen is the AI will be unsure. It will give me, you see how it gives percentages where here it says 100% a plane. It will tell me this image, from what I can understand, looks like it could be 30% a car, it could be 70% a plane, or vice versa. It will give you a rough percentage of what estimate. Like based on what I'm seeing, there's a 30% chance this is a car, but it's also a 30% chance this is a plane. So it depends on how you Photoshop it. Assuming, let's say, for example, I have this plane. Let me open a plane. I have this car, for example, and this car has wings on the side. It could confuse the AI and say, okay, fine, I see features of a car like wheels, headlights, but again, I'm also seeing wings, which is associated with the plane. So maybe it'll say, based on this, I'll give it a 20% chance of being a plane and a 80% chance of being a car. That's how it'll handle data it's not sure. I'll see if I can quickly find an image it won't recognize. Let me prepare that. For the question of how do you select the number of images that are enough to train, it's a very tricky one. The way I would say it is as much as possible. 2 images is not necessary. It is too few, but for the simple reason that if I come back here and just open my cars, for the simple reason that if all I've shown it are, yes, exactly. If all I've shown my AI are cars facing sideways, and you've trained with the 2 images of cars facing sideways, when it comes across a car like this that is facing an angle, it will be confused because its understanding of a car is a car has to be facing sideways. Whereas now by giving it 20 images, I've told it a car can face left. You can have 2 cars in one photo. I've told it a car can face sideways. I've told it a car can be on the road, if that makes sense. So the more data or images you have, the better. And it's why, as soon as Mr. Abu said, it's why there's such a heavy push for companies to be just harvesting as much data as possible, whether it is from our daily lives, from our social media browsing. Companies want a lot of data because the more data they have and the higher quality data they have, the better the AI models they can train. Can you give another car from a different source? Yes. So the test data I had, if you see my test data, I know I'm going through them quickly. These cars are not in my training data. So you can see this is a blue car, I think that's a GT, maybe GT86. But you see this blue car will not be in my training data. So in our training data, we don't have any blue car at all. So technically that blue car, it had never seen it before. It's first time seeing that blue car. But yeah, that is the bulk of it. Like I said, there's a lot of ways you can do it. I know this one is a simple image sorting algorithm. There are other ways you can have, even if it's simple AIs that are effective. For example, 2 days ago, I got an SMS telling me, oh, to go and pay a parking ticket. But because I knew I hadn't parked illegally anywhere, like in a very long time, I was like, okay, fine, this has to be a scam. But I was trying to find, okay, fine, what convinces me it's a scam? I searched, it took a long time, even though I knew it was a scam. I was searching, because when you click on the website takes you to looks identical to the one where you would normally pay on, the gov.uk site. So I was trying to figure out, okay, fine, how can I decisively convince myself that? And I also saw the URL, because the URL was some funky URL. Let's say .jump.com, for example, and obviously a official government site will be .gov. So even I that knew it was a scam, it took me so long trying to prove to myself it was a scam. Imagine someone who may not have known it was a scam, maybe an elder generation. Maybe I have a grandma who is maybe 60, 70, and she doesn't have the expertise to know that, okay, fine, check the URL, check this. If I have a simple artificial AI where I've trained it on how to identify spam messages and scam emails, I've sent it maybe 1,000 scam emails. I told it all the scam emails, understand what comprises a scam email. Then I can also, okay, fine, anytime you receive an email or a text, this AI will help you tell, okay, fine, is this person asking you for money truly genuine, or is it a scam trying to rip you off type of scenario? So there's so many different ways that even just simple basic AI concepts can be used to tackle real world problems, so to speak. Even this image sorting one, to be honest, but let me not carry on any further. Thank you for your time, and I'll pass on back to Mr. Ashe.
Thank you very much, Joshua. This is a wonderful one. If there's nothing I've taken from this section, the link you've given to Ross to go and start exploring is one great thing. And I think you've dealt with the neural network, which was one of the questions of one of the people that participated. We also have question on relating to question relating to tokenization and passing, which you mentioned along the line. Now we have the tokenization, linking it up to other, is it lematization or so? Well, we'll get to master these vocabularies with time. I want to believe that tomorrow we'll be diving straight into the practical section and also looking deeper into how we explore.
Not tomorrow, Thursday.
Pardon me, on Thursday. Yeah, so please let's take the opportunity to prepare our questions and go through the materials we've given. This message is recorded. I mean, the presentation is recorded and it will be presented to us on CREED website, so you could go there and utilize it. I want to thank everyone for coming. I want to thank Cabo and also Joshua for the time you spent. And I want to apologize to all of us because we started late. We have some teething issues, and that was why we lasted this far. The plan was for 1 hour. Tomorrow, Thursday, we got 2 hours, full 2 hours practical section. And I believe you all enjoy it. Thank you very much for coming. Do we have any question that wasn't in the chat box? I mean, the chat, I'm speaking AI now. Is there anyone having a question that has not been answered in this sense, which we could tackle quickly?
Sorry, not really a question. You talked about materials. Where are the materials?
Okay, there's a link. You have if you go to your chat section, we have a link there, teachablemachine.withgoogle.com. Teachable Machine. Just click on your chat, you find it there, copy it,
okay,
and you go in straight into that.
Okay.
Thank you, Edith.
Thank you.
Thanks. Okay. All right. So I want to thank everyone for your time once again. On Thursday, we'll be meeting same time, and we have more understanding of what AI entails by the grace of God. Thanks for your time. God bless you.
Thank you. God bless you too.
Thank you very much.
Thank you.
Thank you very much.
Thank you very much.
Thank you very